Hi, I'm Hector. I've spent about 10 years designing and bringing up embedded hardware and firmware, everything from schematics and PCB layout to SoC bring up and factory RAM. I've worked on industrial gateways, IoT, low power sensor nodes, IP camera, and production readiness at companies like Circom, Compound, and Foxconn. What I enjoy most is getting my hands dirty, solving the hardware problems that only show up once you are in the lab and are on the production line, and then working with firmware, mechanical, and factory teams to make a product reliable at scale. I'm excited about this role because you get to build rugged, real-world devices and own the whole delivery. That's where I make the most impact. About the second question, is designing a sensor for harsh conditions. Um, if I'm building a sensor that has to survive heat, vibration, and moisture, I think through it in three layers: the electronics, the enclosure, and the software. Firstly, electronics. I pick industrial grade parts and derate them. That immediately buys reliability. Power design is critical. Proper PMIC sequencing, surge protection, and solid decoupling so sudden current draw doesn't brown out the radio. For signal lines, I add series resistors, common mode chokes, and TVS diodes where needed. Secondly, the PCB and enclosure. Layout matters. Continuous ground plane, thermal vias for hot components, and placing sensitive parts away from mounting holes. For the enclosure, I design to an IP rating, use proper gas gasketing and corrosion resistance materials, and add strain reliefs for cable entries. For vibration, I use rubber dampers at mounting points and avoid long cut edges that can crack. Thirdly, firmware and validation. Implement watchdogs, transactional storage, and buffered telemetry so the device survives flaky networks or power cycles. An OTA mechanism and robust recovery path are a must, and don't leave testing to the end. We need to run pre-compliance EMC checks, um, halt, has vibration, and thermal cycling early, and do a pilot production run to catch assembly issues. So in summary, pick the right components, design the PCB and enclosure for the environment, and make the firmware resilient, and validate early with a targeted test. That combination is what keeps the devices reliable in the field. About the third question, uh, to explain LoRa and Zigbee to a non-tech PM. Here's a simple way. I'll explain it to a non-tech folks. Imagine two ways of communicating. One is a whisper that travels very far but only occasionally. The other is a neighborhood mesh where people pass notes quickly between neighbors. LoRa is a whisper. It goes far on very little battery, but it's low bandwidth. Great for devices that send tiny updates rarely and need multi-year battery life. And Zigbee is a neighborhood mesh. Each device talks to its neighbors and relays messages. So in a dense site, it gives a very reliable local coverage and lower latency. But devices use use more power, and the mesh adds complexity. So the trade-offs are range and battery life, like LoRa versus mesh resilience and higher meshes frequency is Zigbee. I usually advise a quick site pilot test in interference, gateway placement, and battery life in the actual environment, and then decide. If your priority is remote devices and multi-year battery life, so we choose LoRa, and if we need lots of sensors talking frequently in a plant, we choose Zigbee. And the final question is about an unexpected technical challenge and how to fix it. In one project, we were doing a bot bring up for a gateway and started seeing random reboots and intermittent radio dropouts on the production line. It was intermittent, so it was blocking pilot production and very frustrating. What I did first was to reproduce the issue reliably in the lab and gather data, serial logs, power rail probes, and packet captures. So and then I isolated subsystems. I disabled peripherals one at a time to see which domain triggered the fault. The oscilloscope showed micro dips on the 3.3 volt rail that coincided with a radio burst that pointed to a power domain transient. So I hypothesized either insufficient decoupling or poor power sequencing. I redesigned the decoupling, added low ESR block caps, moved high frequency caps right next to the radio's BDD pins, and added an RF ferrite to isolate the domain. I also adjusted the PMIC sequencing to delay radio init until the regulator was stable, and I added a watchdog and a radio re-init path in firmware, so the device could recover if a glitch still happened. Then I validated with 72 hours burn-in under vibration and thermal stress. The reboots disappeared on both lab and production units. I documented the RCA root cause analysis and updated factory SOPs so the line could catch similar issues earlier. It saved a bot respin and fixed a major yield blocker. That story shows how I combine measurement, isolation, and a hardware fix plus firmware safeguard, then lock the fix into production processes so the problem doesn't come back.